Hi there. Today I'm going to have a look at capacitors in series and in parallel. I want to do this so that I can understand what happens, what's the difference between putting them in series and putting them in parallel. Is it going to change the capacitance somehow? Supposedly it will do. So let's go and do that. Let's go and have a quick look at the mass and then put it on the breadboard and see what actually happens. Okay? So capacitors in parallel and capacitors in series. Well, actually the mass for these isn't that hard, because if we've got four capacitors, which are these ones, so that I've got 4,000 microfarad, which if I'm right is equivalent to 1 millifarad, then when they're in parallel the equation is this. Now if it looks familiar, it is, because that's the same equation for resistors in series. So if you've got, like I've got there, 4 resistors and they're all in, and they're in parallel, and they are 1000 microfarad times by 4, because they're all the same, I can just do that, 4, or you can say 0.001 plus 0.001 plus 0.001 plus 0.001 for 0.001 times by 4. There you go. That's 4,000 microfarad. Very simple. So you increase the amount of capacitance when they're in parallel. When they're in series, you've got to use this equation. Again, does it look familiar? It is, because that's the same equation we use for resistors in parallel, but this is capacitors in series. So the way that capacitors work as far as parallel and resistance and series go seems to be the opposite to what you'd calculate for resistors. Now I've got 4 capacitors there, equals 0.001 of a farad. They are, let's write it down, 1000 microfarads times by 4. So if I actually have them in series, I've got to say 1 divided by capacitor 1 plus 1 divided by capacitor 2 plus 1 divided by capacitor 3 plus 1 divided by capacitor 4. Slightly different way of writing that, I can write capacitor 1 over capacitor total equals 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3 plus 1 divided by C4. Quite simple. Same as if we were doing it for resistors, only we've got capacitors in series. So 1 divided by 0.001 equals 1000. That's great, because we've actually got 4 lots of 1000. So that's just 1000 times by 4, 4,000. But that's not quite there, are we? We've got to finish the equation off, because it's 1 divided by capacitance total. So we've got to have 1 divided by 4,000, which equals 0.00025. So that's basically saying that we've got 250 microfarad. Or if I'd taken the 1000 microfarads that I had and divide it by 4, because that's what I've got, very simply we'd have 250 microfarad, which is proved by the equation there. So simple enough. Capacitors in capacitors in parallel and capacitors in series. So let's put it on the breadboard and have a look. So here we go. Here's the 4 capacitors in series. Got me 2 multimeters for the voltage and the current, and I've got 3 volts on the power supply. I'm going to charge these up and see how quickly they charge, see how much current I get flowing. Here we go. About what, 380 microamps. It's almost at 3 volts. It's charging very quickly. There you go, 3 volts already charged. Didn't take long at all. But that obviously suggests to me that these 4 capacitors aren't holding all that much charge. So let's turn that off and connect up to the LED and find out what happens. And look at that, the briefest of brief flashes. The current's all gone, the voltage is right down again, so there's not much in these. So as I calculated earlier, and you saw earlier, these, when you have them in series, don't hold a great deal of charge. I mean, they're 25 volts, so I could turn the voltage up. Let's do that actually. Let's turn the voltage up and see how much more they can hold if I have a higher voltage. I'm not going to discharge them, there is a small voltage left on there. So turn it on. Look at that, just over 1 milliamp. It's very quickly charging up. It's nearly at 12 volts. There you go, the power supply shows just over 12 volts. So all but charged. So there's still not a lot of charge in that. So let's turn that off. Connect over to the LED. I suppose I could put a switch in there and use the switch like in the diagram, but there was a bit more charge in that, but again it wasn't that much. Still only had about 1 milliamp on of current through the circuit before these capacitors have discharged enough that they can't do anything anymore. There is a little bit of voltage in there, but not a lot. So let's change these round and put them in parallel and see if what effect that has. So as we calculated earlier, it does show that when you have them in parallel, effectively you just add all the capacitance up together. So if I've got 1000 microfarads, I'll end up with 4000 microfarad. So let's go and shift these round. So here we have the capacitors now in parallel. So let's see what we get out of this. Am I going to have to turn that up? I don't know. There's a tiny bit of residual voltage in there. Let's not worry about that for the moment. And let's turn it on, see what happens. See how the voltage is rising much slower. I've got the volts back on 3 volts, so a 3 volt input, but this is taking much longer to charge up. Now this only started about 300 milliamps or something like that, microamps, but the current is still flowing because these 4 capacitors are all being charged. 2 volts. So as you can see, the time frame for 4 capacitors in parallel is much longer than 4 capacitors in series. Slowing right down now on the charge, 2.5 volts, 67 microamps, and it's still going up very slowly. I mean, if I was to have timed that, you know the difference. Well, with the capacitors in series, it take what, a few seconds, 30 seconds, This is taking much longer to reach the 3 volts. Still getting there. Current, as you see, the current is slowing down. Like we saw in the previous video where I'd shown you that graph with the voltage going up and then the current coming down, current flow reducing as the voltage reaches its maximum. So these capacitors will soon be at the supply voltage. And we're nearly there, but like I say, it's taken some time to charge up the 4 capacitors. Nearly. Current's all but gone. 0.97. Now, am I actually going to reach the 3 volts that I'm putting in, or is it just going to sit there? It's just going to slowly trickle and charge these capacitors until you get to the point where it just won't charge anymore. Will it actually reach 3 volts? I don't know. 2.98. Is it going to come up at 2.99? Perhaps we might actually see 3 volts. That's what I'm hoping for. So the charge time is in the range of minutes, where for these capacitors in parallel, whereas in series it was seconds. Is it going to give me 3? Oh, there we go, 3 volts. So let's turn the supply voltage off, connect this meter over to the LED so I can show it discharge. So 4 capacitors in parallel. There you go, the LED is on, and it's on for much longer. It takes much longer for the current to discharge through the LED. The other thing you can see is that it still comes down to about 1.5 volts. At that point there seems to be no current left, and that voltage is not going to drive anything round through this circuit. So the LED is basically off now, and it's say that they're discharged. Of course, if you wanted to fully discharge them, you can do just by shorting out the pins of the capacitor. So let's change that back over. Let's put a bigger voltage in. Let's turn that up to 12 volts. I suppose 9 volts would be sensible because we get a lot of circuits with 9 volts. So let's do 9 volts, okay? And turning that on. Went up to literally just under 1 milliamp. As you can see, it's rising. It's obviously rising quicker than to 3 volts than it was when I was just putting 3 volts in, but it's still rising quite slowly, and I'm charging this up to 9 volts now. These capacitors are the same ones I used before. They're 25 volt, so they should easily handle 9 volts, but it will take some time for these capacitors to fully charge up. Come up on 7 volts. There we go, 7 volts, just 280 microamps, 7 volts. So I can imagine this will take quite some time to actually get to 9 volts. Again, in the range of minutes, not seconds. I'm close enough. I can't wait any longer. 9.7. So let's turn this off. Connect this over to the LED part of the circuit. So without there being any supply to the LED, it's all coming from the capacitors. There we go. It got over range on the current, so it's more than 2 milliamps. It has very quickly discharged, but not that quickly. But it's the fact that there was a lot more current that was able to flow through this circuit before it was discharged enough that it's not really. Well, the LED is still on slightly. and again we still got a small voltage. So there you go, the basic fact that if you've got capacitors in series, you reduce the total capacitance, but if you have capacitors in parallel, you increase the capacitance, which is the opposite way around to what resistors do. But unlike resistors, capacitors are holding on to a charge and then giving it back out. Nice and simple, really. There you go. So there you go, that's capacitors in series and in parallel. As you can see, the equations for series and parallel are the same as that for resistors, only the other way around. So basically, if you've got multiple capacitors in series, I can't really think of a reason for doing that actually, you'd end up with less capacitance, unless you've got a bunch of large capacitors but you want a smaller capacitance. And then capacitors in parallel, you see that all the time, see that quite a lot. You want to increase the capacitance, so you put them in parallel. I'm sure there's lots of uses I'm going to come across that I'm going to see that application of capacitors. So there you go, capacitors in series and parallel. So if you like this video, thumbs up, subscribe, and I'll see you next time.